Now I'm recording. Okay. Okay, to our audience on the video, we don't know how long we stopped recording. It started, but it went and filled up the memory quick. Alright. Wow, where in the heck was my brain? Oh, I have to restart the computer, that's what it did. Number 6. Okay, we're doing number 6. Okay. Particle moves along the x-axis so that at time 0 its position is given by this position function, x of t. At what time t is the particle at rest? Well, I'm at rest when the velocity is 0.
Oh my gosh.
So it's just a matter of taking the derivative, saying equals 0 and factoring.
You know what the sad part is that I divided 72 by 6 in my head wrong. I couldn't do it. I can't do mental math.
Right.
Because I got 13.
This should be, so being a non-calculator question, it should be a factorable thing you can do.
Yeah.
If they give you something that's going to require a quadratic formula on the non-calculator part, you probably made a boo-boo like dividing by 6 wrong or whatever.
Yeah, I know
Oh my
about
god. Did you get 13?
Well, no, what I did was, instead of, I said 6 went into 42 8 times. And so I got critical numbers of 6 and 2.
Doesn't mental math suck?
Wow.
I was afraid, like I was like, T equals 3 and 4, I was like, oh, but 7 halves is on there twice, that's gotta be one of them.
Alright, now, I'll tell you what, we've got another 30 minutes. Let me...
I feel like these questions are easier than the questions we've been doing.
Yeah,
These questions are more straightforward. You're like,
Yeah.
take the integral of this, and the AP questions are like,
Like I got
hey,
These are
all
AP
this
questions.
stuff is secret.
These are AP questions off of old exams. That's where they came from.
1970.
So I guess we're hoping for...
What, Brenda?
Why did the questions get harder get fucking? Like, they just put more words in there and it's really stupid.
Brenda thinks it's stupid.
They put more
guys.
words in there and it's really stupid. Okay, I will make sure and pass that on to the chief reader of the AP exam. Less words, please.
The chief reader, is that like this?
Yep.
Math is supposed to, like,
That's like being declared like the world's biggest nerd.
Hey now.
I'm sure there's more.
Now, hey guys, you guys, many of you know Austin Anderson?
Yeah.
His dad is the chief, has been the chief reader for the AP Statistics exam for several years. From Center College.
I think there's more nerdy things to be in life. Like, I don't know.
Okay, let's do this. Here, turning to number open response 2006 question 4.
Lee, I didn't say it was a bad thing.
So 2006 question 4. Let's take the time to work through this guy together.
Yay!
Now, I want to do this because as I look at this problem, just on first glance, it looks pretty rich in that it's going to be motion stuff and it's got a table of values. That incorporates a couple of different style questions in one. So let's see what we got. Rocket A has positive velocity after being launched upward from initial height of 0 feet. Okay, it's on the ground, shooting up. At time t equals 0 seconds. Okay. The velocity of the rocket is recorded for selected values of time over the interval 0 to 80 seconds, and they're in the table up there. Okay. We got that. Now, alright. Time t's and velocities at those times. Now, part A. Find the average acceleration of rocket A over the 80-second time interval. Indicate units of measurement. So, ponder, think. Hunter, Matthew, ponder and think, part A. No.
Positive thinking.
It's not a calculator, but again, we're thinking about how we need to do it, not whether I could use a calculator or not. There is a statement in that question A that tells us how to do it.
Average acceleration.
Average. The word average tells me what to do. There are 2 different theorems we've learned this year that deal with average. What are they?
1 over b minus a. I don't know what it's called.
Mean values and average.
Average value of a function.
Okay.
So, okay, so what Nicole was mentioning is 1 over b minus a times the integral from a to b of f of x dx. Okay, this will calculate the average value of whatever the f function is. What is it they want me to find the average value of?
The acceleration.
Do I know the acceleration function so that I can integrate it?
No.
Can't use this guy then.
Sure.
Now, what other theorem did we learn that deals with the word average? The mean value theorem. The mean value theorem says, well, if you guys remember the wording, if f is continuous in the closed interval and differentiable in the open interval, then there exists some c on the interval ab such that f prime of c equals f of b minus f of a over b minus a. This says there is some time t, in this case, where my instantaneous velocity equals my average. Okay, now, but I don't want average velocity, do I? I want average acceleration. So I've got to get the change in velocity over the change in time. Because what are the units of acceleration measured in? Feet per second squared. Feet per second per second. So if I think about my units, this guy needs to be measured in feet per second. Oh, that tells me what to do exactly right there. Because this is going to be feet per second, so these have to be velocities over seconds. Those have to be times. So my average velocity on this 80-second interval is going to be, my average acceleration is going to be the velocity at 80 minus the velocity at 0 all over 80 minus 0. The change in velocity over change in time. Now you recall, our notation, delta v over delta t, the change in velocity over change in time, that was average over some interval. Eventually, when we learned the calculus stuff, that rotated or changed to dv dt, the instantaneous velocity at 1 instant. So this is what we're doing. What's the velocity at 80? 49. What's the velocity at 0? All over 80. And I can leave my answer right there. Or it would be, what, 44/80ths?
11/20ths.
When you
Okay.
like units of measure and whatnot.
Yeah, and we do indicate units of measure, which we've already discussed, so what are they? Feet per second.
Yeah,
Per
I
second.
prefer, I like feet per second.
Should we not say what that is?
Someone's
Well, what do you mean?
Average
Like,
acceleration.
interpret it somehow?
Well, like, we just kind of put an equation out there.
Like average growing,
Well,
like a water.
You could, I mean, yeah, it's implied what it is I'm finding here in the prompt, but yeah, sure. We can say average acceleration is, and they've already said on the time interval, so. I guess if you're really, really, really meticulous or whatever you say, on the interval 0 to 80, the average acceleration is, and then work it out. Okay? So, key phrases. Average. That should send a big red flag up and say either, as Nicole said, average value of a function, or, I think she said it again, mean value theorem. Okay?
Sorry.
Okay. Now, part B. Using correct units, explain the meaning of the integral from 10 to 70 of v of t dt in terms of the rocket's flight. And then use a midpoint Riemann sum of 3 subintervals to approximate this. All right. So again, ponder and think. What will that integral calculate for us?
Displacement. Yeah.
Bingo. Displacement. It'll be displacement. If it was absolute value of velocity, it'd be total distance traveled. Now, thing is, let's decide which one it'll be, because we can analyze this a little bit. In terms of my rocket's flight, at time 0, my velocity was 5. Then I sped up, sped up, sped up, sped up, sped up. I'm increasing the whole time, aren't I? So, which way's my rocket flying the whole ding dang time? Is it ever reaching its peak and then falling back down? No, because it never started slowing down, did it? All right, we convince ourselves of that without doing any calculus, you know. So, in terms of the rocket's flight, let's just say this. I mean, Hunter, you're absolutely right. It is going to be displacement. So the distance between the position at 10 seconds and the position at 70 seconds. Well, a way to think about this, watch. If I integrate velocity, I don't necessarily have to do this on the test, but I'm just showing you. If I integrate velocity, what will it give me? No, that's derivative. Position. And this is a position in the y direction, right? So I would call it, it's going to give me y as a function of t. Because I'm not moving horizontally for x, I'm moving y. So, but I'm going to evaluate that from 10 to 70, right? And that's going to give me the y position at 70 minus, whoops, the position at 10. Oh, the difference in the position from where I stopped to where I started. That's displacement. So, okay. So, right now, explain the meaning of this in terms of the rocket's flight. It's going to be the displacement of the position of the rocket from time t equals 10 to time t equals 7. Or we could also say it will be the total distance traveled by the rocket from time t equals 10 to time t equals 70. I can say total distance traveled because my velocities are all positive increasing. Written doesn't like that. Okay. All right. Now, let's see about the Riemann sum part. I want to do a Riemann sum of 3 subintervals to approximate this. Now, somebody out there said earlier, area. I heard him say area. And sure enough, I will think of this as area under the curve in this Riemann sum. I want to go with 3 subintervals of equal length. So let's look at our table of values. From 10 to 70, I want 3 subintervals of equal length.
Oh, it was only from 10 to 7.
And I'm doing a midpoint Riemann sum. So yeah, we're going to go from 10 to 30, maybe. Wait.
Yes. Yes. 10 to 30, 30 to 50, 50 to 70. Yes.
Oh, yeah.
Yeah.
That'll give them all.
10 to 30, 30 to 50, 50 to 70. Yeah. And the midpoint is going to be here, and here, and here. So, I'm going to approximate this guy by the area of 3 rectangles. And one of them is going to be the height of the first rectangle at its midpoint, which would be what value? 22. That's the function's value at the midpoint times the width of that interval, which is how big? 20. Plus, what's the value? Okay, 35 is the height of the second rectangle times the width of 20. Plus the height of the third rectangle is 44 times the width of 20. It's a non-calculator problem. I'm done. I'm not going to simplify that son of a gun.
I can't.
All right?
Yes,
I can't just.
Now,
Yes, because you can.
and did it ask? Oh yeah, it does say using correct units. So that total distance traveled will be in what units? Feet. I needed to include that in my statement earlier. It'll be the distance traveled in feet of the rocket from time t equals 10 to time t equals 7.
What sum is it when you have to do like the number of intervals you have to multiply that out in front? I'm talking about.
You're thinking about a Simpson's rule or trapezoidal rule, where did that b minus a over 2n?
Yeah. That's.
We won't see that format on the test here. When you're asked to do a trapezoidal sum, you're going to physically begin the table of values, and you're going to add up the area of the trapezoids. You're going to actually geometrically calculate their areas. Yes, sir.
Yeah, that's what I did on last night's homework. I did the 1, 2, 2, 2, 2, 1 thing.
Okay.
Instead of the actual area.
When they give you a table of data or a picture of the curve where you can get those y coordinates, the table of data is where you're going to see it a lot. It's going to be a geometric adding up of the area of trapezoids. Yes, sir. Yes, sir.
How long will we have to do the 6 open responses for this?
Basically 15 minutes apiece. You'll be given the 2 open responses with graphing calculator and have 30 minutes. Then you'll be given the other 4 open responses. They'll say put your calculator away, and you'll have an hour to do those. You may go back and work the previous 2, but you cannot get your calculator back out. You better check on Mr. Duck because he'll back again for that.
That's my mom's room.
Is that your text message, Tom?
Is this where you do all the
My mom
sounds?
has already cooked this for me. I don't know why.
No.
Like, why did she choose the duck?
Me, you look like a duck. It's not a bad thing.
Wow.
It's just a duck.
Thank you.
That's not a bad thing.
Okay,
Maybe small.
let's take a look at part C. Ready? Now, this is very often the format of a lot of these questions. They'll ask you a part A, B, or something, maybe even C, about the data stuff. And then they'll kick in and they'll throw an equation at you. This guy says rocket B is launched upward with an acceleration of this. 3 over the square root of t plus 1 feet per second. It's acceleration. At time t equals 0, the initial height of the rocket is 0 feet. Okay, so launched from the ground. And the initial velocity is 2 feet per second. Okay, so I've got an initial velocity which will let me find my plus c in the velocity function. And I've got an initial position which is going to let me find my plus c in the position function. And it says, which of the 2 rockets, okay, is traveling faster at time t equals 80 seconds? So I need to compare their velocities at 80 seconds. Don't I? Well, I know the velocity of rocket A at 80 seconds. It's 49. I need to find the velocity of rocket B at 80 seconds. What do I got to do? Got to integrate. Let's do it. So, the velocity at time t is going to be the integral of acceleration, and that's going to be 3t plus 1 to the negative 1/2 dt. Do you need a u substitution?
Yeah.
What would your u be? T plus 1. What is du? 1 dt. So I can just say this is 3 times the integral of 1 t plus 1 to the negative 1/2 dt. This is of the form u to the 1/2 times du, or negative 1/2 rather. So I can integrate it. B as the function of t is going to be t plus 1 to the what power? How much? Now, yeah, positive 1/2. Then divided by 1/2 means I'm multiplying by 2, so I get a 6. Plus c. How do I find my plus c? Right. The velocity at time 0, and here's where we got to be careful. The velocity at time 0 is going to be calculated by this. And that velocity is 2. This is one of those instances when I put 0 in, it doesn't just make everything go away. I've got to actually work it out. Because 0 plus 1 is 1, not going to be 0. So that gives me 1, square root of 1 is 1, plus 6 is 6. So c is going to be negative 4. When I subtract that 6 over here. So now I've got the velocity at any time t is 6t plus 1 to the 1/2 minus 4. From here, I can find the velocity at 80, can't I? Oh, looky, they gave us a nice number.
Yay.
That's going to be 80 plus 1 is 81, and I can square root that. That's going to be 9. 9 times 6 is? How much? 54 minus 4 is? 50. Which of the ones is traveling faster?
50 is bigger than 49.
50 is bigger than 49. So, again, which of the rockets is traveling faster? Rocket B is traveling faster since?
Its velocity is
The
above the
V of 80 of rocket B is greater than
Wait, where is it?
So, we're going to have some statement saying rocket B is traveling faster at t equals 80 seconds since V, and you might even say V sub B of 80 is 50. Velocity of rocket B of 80 is 50. And velocity of rocket A of 80 is 49. So therefore, since velocity of rocket B is greater than velocity of rocket A, it's traveling faster. Done. Now, why do you think this was even in there? Initial height is 0 feet.
Really, 49 or 50?
distractor.
It's kind of a distractor, but it's also necessary to know
They started
they were both launched from the ground. If Rocket A had been launched from the ground and Rocket B had been launched from the top of the Empire State Building, different stuff going on.
But wouldn't it still be traveling? Wouldn't the velocity still be the same at time 80?
In a perfect world, no, because there would be slightly different accelerations of gravity for different heights. It's so negligible that we don't usually count in our calculations that it is there.
But in our little calculus world,
Yeah, I think it should be still the same scenario. Yeah. But I think we got to consider this sort of stuff. Especially, Megan, if they'd gone on to say, you know, somehow we had enough information to say what's the height of the rocket at 80 seconds. Then I definitely want to know if this one started here versus it started up here.
but that wasn't the question.
I know, I'm just saying. It could have been.
But it wasn't.
I know it wasn't.
Vivian, you're so sassy.
All right.
I had 3 things in soda today. I don't even drink soda. I'm like strung out right now.
Was I saying it wrong?
I don't like my students being strung out this way.
You shouldn't have said it.
I know. All right. Let's finish up our last 10 minutes here. Let's get on our multiple choice. Let's see what you guys can do real quick with 7 through 10. These are with, I do believe, indeed with calculators. Yes. Anybody does watch this video, they're going to really wonder what's going on over there.
I'm too tired.
Okay. Let's see how we did here. Pull this down. I just noticed the camera's got a nice big shiny spot in the glare, but that might be a little better. All right. For number 7, I got E.
Oh, I was wrong.
Number 8, I got B as in boy. 9 is C as in cat. 10 is D as in dog. And just for you to know, if you want to work them later, 11 is C and 12 is B.
Yeah, I tried to do 11 and I had no idea.
Okay. All right, here we go. Number 7. I've done the following here. The data for acceleration for 0 to 6 seconds are given. If velocity is 11 at time 0, approximate the velocity at 6. Now, again, they're wanting the value of a function at one number, and they gave you the value at a different number. That's doing this type setup here. If I integrate acceleration, I get velocity. If I integrate acceleration from 0 to 6, I get the velocity at 6 minus the velocity at 0. The velocity at 6 is what I wanted. Add velocity at 0 over. I know the velocity at 0 is 11. And then this in the brackets is my left Riemann sum. The height at the left interval, 5 times the width of 2, plus the height at the left interval, 2, times the width of 2, plus the height at the left interval, 8, times the width of 2.
And how'd you plus 11?
That was my v sub 0 added over here, and they told me the velocity at t equals 0 is 11.
Okay.
That was where I came from. How about 8? Well, you had to integrate acceleration to get velocity. Because I want to find out when is velocity 0, so I need my velocity function. So I integrate velocity, velocity is the integral of acceleration. I integrate acceleration, I get velocity plus c. I use my initial condition that says at 0 the velocity was -2. So at time 0, velocity was -2. Again, this is one of those cases where don't think just because you're putting 0 in, everything disappears. Cosine of 0 is actually 1. So I get -2 equals -1 plus c, add it over, c is -1. There's my velocity function, and I want to know when is velocity 0. Put that in my y1 and look for x-intercepts. Looking at the next two. This one was total graphing calculator, 9. They gave me the velocity function. They said, what's the acceleration at time 4? It's the derivative of velocity at 4. I put the velocity function in my y1 screen and said, second, calculate the derivative at 4. And I gave you that number. And just knowing what to do. Part number 10 there. 10 says position of an object attached to a spring is given by this y function. So that gives me the y coordinate of any of the object attached to the spring at any time t. Where t is time in seconds. In the first 4 seconds, how many times is the velocity equal to 0? So you can imagine someone on a spring, when it gets to the very bottom, velocity 0, comes back up the top, velocity 0, 0, 0. So how many times does that happen? Well, so velocity is going to be 0 when the derivative of position, which is velocity, is 0. So I had to take the derivative of position. That involves chain rule. Derivative of cosine of u is negative sine of u times du. The derivative of sine of u is cosine of u times du. And I want to say how many times is this 0 on the first 4 seconds. So from there, I got my calculator. I put that, whoa. Where's my light? Oh, there we go. There we go. I got my calculator. I set my window up so that my x minimum was -1, max maximum was 5, because I wanted the first 4 seconds. So I like to see a little left of and a little right of. And my y min and max happen to be -6 and 6 already, so that's pretty narrowed in and zoomed in on my x-axis there. I put that curve, my y prime, my velocity curve, in my y1, and I just graphed it. And I counted how many times this is velocity. How many times is velocity 0? On the first 4 seconds, here's 0, 1, 2, 3, 4. In that interval, my velocity is 0, 1, 2, 3, 4, 5, 6 times. That's it. Now, Hunter, you said you couldn't get 11 no matter what. You want to talk about it while we're here?
Yeah.
Okay, I haven't even looked at it yet. Number 11 says a particle moves along the x-axis so that any time 0, its velocity is given by that guy. The position of the particle is 3 at time 0. Okay, I know an initial position. What is the position of the particle when the velocity is first equal to 0? I need to know when that occurs, don't I? So I'm going to get my velocity function, I'm going to put it in my y1. So I'll just type that in, you type along with me. Cosine of 2 minus t squared. Cosine of 2 minus x squared. Now let's see. Any time greater than 0. Well, I have my window set up from -1 to 5. I'll take a look at that first. Here's my curve. When is it first going to be 0? Well, it's going to be right there for time greater than 0. So I need to find out where that is. I'll say second, calculate the x-intercept with a 0. Second, calculate, choice 2 is the 0. I got an arrow left to get over here. Left bound, that'll work. Right bound, that'll work. Guess. 0.65513. Oh, you guys can't see that very well, can you? 0.65, why is this extra dark today? 0.65513 is where that 0 is. I'm going to save that number. Getting out of this screen, I'll hit store as A, and it's storing that number I just had. That's the time t that I first have a velocity 0, so I want to find the position at that time t. I think my most efficient method, because I can't do this guy by hand. I look at it and I'm already saying if I let u be 2 minus t squared, then du is going to be -2t dt, and I don't have a -2t. So I'm going to do this guy by saying if I integrate velocity If I integrate velocity, I'm going to get position, right? All right, and this is moving along the x-axis, so I'm going to get the position at some time t. If I integrate the velocity from 0 up to my time t I'm looking for, that 0.655, then this is going to be the position evaluated at 0.655 minus the position evaluated at 0.
So that's second fundamental.
Now that's just
Okay.
integrate, that's fundamental of calculus.
You can just use a calculator.
So now I can add this x of 0 back over. So the initial position, now think of it this way too, Hunter. My initial position plus, watch, the total accumulated change in position, which is what velocity is, right? The net change in position.
Yeah.
Will give me my ending position. This is what I'm looking for. This, I know x of 0 was 3. This, I can calculate. I've got that in my y1 anyway, and I'll just say second, calculate the integral from 0 up to the a that I stored.
You know what I did? The number was around 3 decimal places. Hey, Mr. Doggo.
I get negative 1.84.
Hey, they're going to try and be as...
And so that's going to give me something.
So how would you like integrate that without a calculator?
Wouldn't.
Yeah.
Wait, did you say that number 11 was C or D? Okay.
The key gave me
What did you say the answer was?
C.
What about 12?
'Cause I just got 2.816,
Yes.
and that is C.
12 is B.
12 is B as in boy.
Bodacious.
Bodacious. I gotta see what this bodacious stuff was.